You are currently hurtling through space at nearly 560,000 mph on a cosmic merry-go-round. So vast, the light takes 100,000 years to go from one end to the other. We call this a spinning island of 400 billion stars. We call our home the Milky Way, yet we've never seen it from outside. We have never taken a step back to see its actual scale. Tonight, we'll travel to the boundary of our cosmic neighborhood and learn that everything we thought we knew about size was incorrect. Distance and our position in space are only the beginning. If you love this cosmic adventure, please hit the like button and join in. Prepare yourselves. We begin. Astronauts frequently describe the first time they glimpse the Earth from space. They look through the tiny spacecraft window for recognizable landmarks and cities that appear gigantic from the ground, appear like scattered spots of light, mountain ranges that took hours to drive across, stretch beneath them like crumpled paper. They look at the surface below, hoping to see their hometown, street, or perhaps even their own backyard. But this is what surprises them the most. They can't see their house. They can't see a house from 250 miles above Earth. Individual buildings vanish entirely. Human vision's resolution cannot record items that small from such a distance. This shows a deep truth about scale that we rarely contemplate. The International Space Station loses detail as it travels farther away. Entire neighborhoods evaporate. Cities become hazy patches. Countries mix into brown and green stains on the Earth's surface. What was incredibly enormous from the ground becomes impossibly small from space. Now imagine drawing back even further. At 1,000 miles up, entire states become hazy forms. At 10,000 miles, continents begin to merge, forming a blue marble floating in darkness. The Earth, which seemed infinite as you went across your backyard, now fits comfortably in your field of vision. However, the perspective trick works both ways. Just as we shrink when viewed from above, the space around us expands beyond our ability to comprehend the empty blackness that surrounds our tiny world. Stretches in all directions for distances that make the width of the world appear like a grain of sand on an infinite beach. Consider this. If you could shrink the world to the size of a marble sitting on your desk, the nearest star would still be more than 4,000 miles away. That marble would sit alone in an empty space longer than the distance between New York and Los Angeles. The loneliness is startling. This crushing void between particles characterizes our cosmic neighborhood. We live on a small rock surrounded by an ocean of vacuums so enormous that light, traveling at 670 million miles per hour, takes years to get from one site of interest to the next. But we're not alone in this nothingness. We pass through it as passengers on something much larger than a single planet. We go on board a massive collection of stars and worlds that dwarfs our wildest imaginations. We live in a galaxy, but there is a catch. Just as astronauts cannot view their own homes from space, we face an even stranger challenge when attempting to understand our cosmic home. The photons. Illuminating this page marked the start of a trip that makes every human exploration look like a walk. Proxima Centauri, located around a block light from our nearest stellar neighbor, left that star more than 4 years ago. 4 years. The light in your eyes right now began its trip when various individuals had different professions, different songs played on the radio, and the world looked very different than it does now. This light traveled through space for 4 years before reaching you. At this moment, Columbus sailed almost 4,000 kilometers from Spain to the Americas. His contemporaries thought that was an impossibly long distance. They were frightened he might tumble off the edge of the globe. They dreaded sea monsters and never-ending storms. 4,0 miles was the pinnacle of human daring and inventiveness in his day. The light in your room has traveled 25 trillion miles. Allow that number to settle in your thoughts. 25 trillion miles. If you could drive your car at highway speeds for 24 hours a day, covering that trip 7 days a week without stopping for gas, food, or sleep, would take more than 40 million years. 40 million years of constant driving to approach our nearest star neighbor. This displays the full size of our galactic neighborhood. Stars that appear as little pinpricks of light in the night sky are actually gigantic nuclear furnaces, many times larger and brighter than our own Earth. They appear little only because of the astonishing distances involved. Space extends so vast between stars that even light, the fastest thing in the universe, takes years to cross. Our galaxy has approximately 400 billion of these distant suns. Some shine only 4 light-years distant. Others, such as Proxima Centauri, flare from 50,000 light-years or farther away. Each one sends photons into space, sending light across the space toward us. Some of that old starlight left its source before humans existed, while others began its trip before dinosaurs roamed the Earth. When you look up into the night sky, you can see a time machine. You see the past beaming itself throughout space. The stars you see may have exploded decades ago, but their dying light still travels towards you, bearing messages from a universe that no longer exists. This produces an unusual circumstance. We live inside something so huge that it is impossible to observe everything at once. We view our galaxy like ants crawling across the surface of a massive clock, able to investigate tiny bits, but never able to take a step back and see the entire mechanism. Light from the outer end of our galaxy has been coming toward us for 100,000 years, delivering information about distant places. They could as well be in another universe entirely. Imagine you have a single grain of sand between your fingertips. Feel the small weight. Consider how it scarcely registers on your skin. This grain is about 1 millimeter across. You could lose it on the carpet and never find it again. You may expel it with a gentle breath. It depicts one of the smallest objects you can easily hold in your bare hands. Let this grain of sand represent the entire Earth. Every mountain, ocean, city, every human who has ever lived is crushed into this small speck. The entire world is reduced to something you could accidentally inhale. On this scale, how large would your city be? Your neighborhood becomes invisible. Your house vanishes totally. Your city, or even a large metropolitan area such as New York or Los Angeles, shrinks to a small bump on the sand grain's surface. Detecting it requires a strong microscope. But we are only getting started with this activity. If the Earth shrinks to the size of a sand grain, our moon will be a little pebble floating 20 feet away. The sun turns into a beach ball half a mile down the road. Jupiter rises to the size of a giant marble and rolls around 3 miles away from your position. These distances are already above what is comfortable for humans. Half a mile seems manageable. 3 miles is a decent walk, but the nearest star to Centauri is currently 125,000 miles away. You couldn't drive there. A commercial airliner could not transport you there. It would take a rocket ship to reach our nearest star neighbor in this sand grain world. This scale model shows a stunning fact about space. The distances between things in our solar system, which appear impossibly huge, are little compared to interstellar space. We are crowded together in a little pocket of warmth and matter, surrounded by an emptiness so vast that it beggars comprehension. On this scale, our entire solar system fits neatly into a circle about 10 miles across, while the next solar system is 125,000 miles away. The distance between star systems is 12,000 times greater than the width of our local planetary family. Even these astonishing distances pale in comparison to the entire extent of our galaxy. If we keep the sand grain size, Our galaxy is 11 billion miles across. Light would take 16 hours to travel that distance, even at its astounding speed of 670 million miles per hour. However, this comparison fails to express the real oddity of galactic size, because we have only dealt with distance thus far. As you read these words, you are traveling faster than any person ever has. You are not just spinning with the Earth's rotation, which moves you eastward at around 1,000 miles per hour. You are not simply orbiting the Sun with our planet, adding an additional 67,000 miles per hour to your velocity. You're involved in something far more magnificent and violent than any of those common emotions. Our entire solar system accelerates through space at 560,000 miles per hour. This pace transcends human understanding. The fastest jet fighters may achieve speeds of approximately 1,500 miles per hour. The supersonic Concorde passenger jet reached speeds of over 1,350 mph. Space. When rockets escape Earth's gravity, they can reach speeds of around 25,000 miles per hour. But we, sitting completely still in our recliners, fly across the universe at speeds that make all human locomotion seem like leisurely strolls. We orbit our Sun, together with its family of planets, moons, asteroids, and comets, which is what generates this tremendous velocity. Wheels revolve around a gravitational core situated approximately 26,000 light-years away from us. We circle this center like a stone whirling on the end of a string, yet the string spans great distances. That light takes 26,000 years to travel. This orbital motion propels our solar system along a course so vast that completing one revolution takes 250 million years. Dinosaurs had not evolved by the time our solar system occupied this identical place in space. The supercontinent Pangaea was just starting to produce life on Earth, which was mostly made up of basic sea animals. We have made less than 20 trips around the cosmic center. Earth has been around for almost 4.5 billion years, but we have only completed 18 full circles around our galaxy in that time. Our planet is 18 galactic years old. This puts our entire life in perspective, from the first stone tools to space travel. This occurred within less than 1% of a single galactic orbit. Rome rose and collapsed. Civilizations appeared and disappeared. Entire species evolved and were extinct as we traversed only a small portion of our cosmic surroundings. But what exactly is at the center of this massive orbital dance? What huge object has enough gravitational attraction to drag our solar system and hundreds of billions of other stars along in this slow, stately procession? The solution entails something so radical that it bends space itself for the majority of human history. We believed we were at the center of creation. The Earth remained immobile as the sun, moon, planets, and stars spun around us in perfect circles. It made sense. We could sense no movement beneath our feet. We watched celestial objects rise and set like clockwork. Obviously, we reasoned that everything else must be moving while we remained immobile in the cosmic center. This comforting notion lasted until astronomers improved their telescopes and began measuring things more precisely. First, they realized that the Earth orbits the Sun, not the other way around. This relegation stung, but at least our Sun might still be at the core of something bigger. Then, in 1917, astronomer Harlow Shapley produced a finding that dashed even the most modest hopes. Shapley investigated GLO clusters, dense balls of old stars that orbit our galaxy, like fireflies circling a bonfire. He measured their distances and plotted their coordinates in space. What he discovered astonished the scientific community. These star clusters were not centered on our solar system. They didn't even focus on our local region of space. Instead, they concentrated around a point around 30,000 light-years away from us. In the direction of the constellation Sagittarius, our solar system sat far out near the edge of this immense collection, like a cabin in the outskirts of a major metropolitan region. We were not in the center. We weren't even close to the center. We lived in the cosmic equivalent of a rural outpost. This revelation demonstrated that we live inside something considerably greater than anyone had anticipated. Shapley determined that our galaxy is around 100,000 light-years from edge to edge. Our solar system is around 26,000 light-years from the galactic center, placing us closer to the outside border than the middle. If our galaxy were a pizza, we'd reside somewhere out near the crust, definitely not in a prime spot near the center, where all the excellent toppings congregate. Although we were unaware of it at the time, this position is extremely beneficial to us. The galactic center proves to be a violent, dangerous place, packed with strong radiation and gravitational turmoil, an unusual phenomenon that could sterilize any surrounding planets. Our suburban setting creates a peaceful, stable environment in which sophisticated chemistry can evolve over billions of years. But Shapley's revelation prompted a fresh question. If we are orbiting something 30,000 light-years distant, what could possibly be massive enough to gravitationally link hundreds of billions of stars into this vast spinning structure? The answer would not arrive for decades, and when it did, it would be stranger than anyone thought. Astronomers faced an impossible hurdle while attempting to measure the width of our galaxy. How do you measure something when you're locked inside it? How can you know how big a forest is while you're standing between the trees? How do you map the borders of a city while you are unable to leave its boundaries? Astronomers encountered this issue when attempting to determine the size of our galaxy. Harlow Shapley solved the puzzle with a smart trick. He couldn't go outside our galaxy to measure it directly. Instead, he mapped the positions of the glow clusters. These dense balls of old stars orbit our galaxy center like distant streetlights. Shapley understood that these globular clusters ringed our galaxy in a roughly spherical halo. If he could measure the distances between enough clusters and plot their placements in 3 dimensions, he was able to trace the invisible boundaries of our galaxy. The clusters would serve as survey markers, outlining the boundaries of something too huge to observe directly. This necessitated tackling another seemingly impossible problem: estimating distances between objects tens of thousands of light-years apart. Shapley accomplished this by examining Cepheid variable stars, which pulse brighter and dimmer in regular patterns. Amazingly, the pace at which these stars pulse is directly proportional to their true brightness. A Cepheid that pulses slowly shines more brightly than one that pulses quickly. When Shapley observed a Cepheid variable star, this relationship provided him with a cosmic ruler. He could time its pulsing pattern to see how brilliant it was. Then he could compare the genuine brightness to how bright it seemed on Earth. The disparity between the actual and observed brightness revealed the distance, because faraway things appear dimmer than adjacent ones. Using this technique, we measured the distances to hundreds of globular clusters spread across the sky. When he plotted their locations, a pattern appeared. The clusters formed a large spherical region approximately 100,000 light-years across. Our solar system was nowhere near the center of the sphere. Instead, we occupied a position approximately 2/3 of the way to the edge. This measurement astounded everyone, including Shapley himself. 100,000 light-years outperformed all prior estimates of galactic size by a large margin. Most astronomers imagined our galaxy was a few thousand light-years across, similar to the distances between neighboring stars. Instead, Shapley demonstrated that we live in something truly cosmic in scale. 100,000 light-years equates to light traveling at 670 million miles per hour. It takes 100,000,000,000 His measurements have held up exceptionally well. Modern techniques have modified his estimates significantly, but Shapley achieved the basic scale perfectly using devices that appear crude by today's standards. However, Shapley's Gular clusters, we simply mapped the observable borders of our galaxy. Something invisible surrounds us. We cannot see it. We are unable to touch it. We can't detect it with any standard instrument. However, this mystery substance outweighs everything observable in our galaxy by a factor of about 20 to 1, including stars, planets, and gas clouds. Dust particles, and all the regular matter we can see, make up only approximately 5% of our galaxy home. The remaining 95% is made up of what scientists term dark matter. How do we know that invisible matter exists if it cannot be detected directly? Similarly, we know that wind exists. When we are unable to see air, we can witness its impact on other objects. Stars located in our galaxy's outer regions orbit the galactic center too swiftly. They move so quickly that they should break apart and spread throughout cosmic space like mud from a spinning tire. The gravitational pull of all observable matter in our galaxy is insufficient to keep these fast-moving stars in stable orbits. Something else must be out there, something large enough, to provide the extra gravitational pull needed to keep our galaxy intact. This unseen mass forms a roughly spherical halo around our galaxy that extends much beyond the visible starfield disk. Recent studies imply that this dark matter halo spans over 2 million light-years. This suggests that the true frontier of our galaxy extends 20 times further, compared to the visible stars. The vast majority of our galaxy is empty space, filled with invisible particles. We don't comprehend. Consider it this way. If our visible galaxy represented a flashlight beam in a dark room, the dark matter halo would include the whole space surrounding that small cone of light. We dwell inside the beam, surrounded by enormous amounts of invisible mass that we can only sense due to its gravitational influence. This dark stuff doesn't behave like ordinary matter. It doesn't emit light. It doesn't absorb light. It is completely unaffected by electromagnetic radiation. Dark matter particles can travel through normal matter as if it were not present. Every second, billions of dark matter particles pass through your body with no interaction. Scientists believe that the halo around our galaxy contains dark matter that is 600 billion to 3,000 billion times the mass of our Sun. This invisible mass influences the structure and evolution of our galaxy in ways that we are only beginning to grasp. The discovery of dark matter raises fundamental issues regarding the nature of reality. Most of the cosmos is made up of things we can't see, touch, or detect directly. We live in a universe in which the familiar matter that makes up stars, planets, and ourselves constitutes a tiny minority component. But even this invisible aura has bounds, and beyond them lay something even more mind-bending. In 1977, humanity deployed 2 robotic explorers to the outer worlds. Voyager 1 and Voyager 2 are the fastest objects humans have ever sent into deep space. They leave our solar system at approximately 38,000 miles per hour, fast enough to cross the United States in less than 5 minutes. These spacecraft have traveled farther away from Earth than any human creation, sending signals to potential alien civilizations and returning breathtaking sights of distant planets. However, their incredible speed, achieved through careful gravitational assists from multiple planets, is pathetically inadequate. For galactic travel at 38,000 miles per hour, Voyager 1 would take 173,000 years to reach our nearest stellar neighbor if it were actually heading that way. 173,000 years. This is a tenfold increase across the entire history of human civilization. Agriculture, writing cities, empires, manufacturing, and space exploration all evolved in far less time than the journey to our nearest star. However, reaching the next star is only the first stage in cosmic exploration, which will eventually span the entire width of our galaxy. Voyager would have to travel for 1.7 billion years without stopping. This temporal period eclipses not only human history, but also the history of sophisticated life on Earth. When Voyager embarked on such a hypothetical mission, the most advanced living forms on our planet would have been basic bacteria, and algal multicellular creatures had yet to appear. Animals didn't exist. Plants didn't exist. Throughout the billions of years it took Voyager to cross our galaxy, the Earth's atmosphere contained essentially no oxygen. Life progressed from single cells to the complexity of human society. This puts astronomical distances into biological perspective. Evolution from microorganisms to mammals and minds takes less time than reaching our cosmic neighborhood at the quickest speed possible with current technology. This computation assumes that Voyager can sustain its speed indefinitely without running out of fuel, breaking down, or colliding with anything. In truth, both Voyager spacecraft will become silent within the next decade as their nuclear power sources deplete. They will continue to travel through space as dead hunks of metal and plastic, but they will never report back on what lies in the darkness between the stars. The enormous space between star systems results in a nearly perfect vacuum. Voyager meets fewer than 1 atom per cubic centimeter in the interstellar medium. This indicates a vacuum that is more complete than anything created in earthly laboratories. The spaceship travels through such empty regions that it may not contact another solid object for millions of years. This nothingness defines the structure of our galaxy. Stars cluster in a flat disk, yet vast distances divide each point of light from its neighbors. However, our galaxy is much more than just a collection of individual stars dispersed throughout empty space. Our galaxy contains more stars than the number of grains of sand on all of Earth's beaches. Our cosmic neighborhood contains 400 billion stars. 400 billion. This amount is beyond human comprehension. Counting one star every second, 24 hours a day, would take more than 12,000 NAR0000. To finish the census, each person on Earth would need to count approximately 50 stars. These stars come in an incredible variety of sizes, colors, and ages, with some shining, blue, and white, and deplete their nuclear fuel in just a few million years. Others glow red and slowly sip their fuel, allowing them to continue blazing for hundreds of billions of years after our sun dies. Some stars have barely enough mass to support nuclear fusion, while others contain dozens of times more matter than our sun, in tremendously dense, extremely hot stellar cores. The variety goes beyond only size and temperature differences. Some stars exist in pairs that orbit each other in graceful gravitational dances. Others join together in dozens or hundreds to form star cities, where strong radiation and gravitational interactions produce strange phenomena. Some stars pulse with regular patterns, acting as cosmic lighthouses, sending beams throughout space. Among these 400 billion stars, at least 100 billion planets orbit in habitable zones where liquid water might exist, with an additional 100 billion, possibly habitable worlds spread around our galaxy. Some of these worlds may have life, civilizations, or intellect smart enough to consider the same questions we are now investigating. Our galaxy's oldest stars, created more than 13 billion years ago, when the cosmos was still young. These old suns have watched the entire history of cosmic evolution, from the days when heavy elements were rare to the present era of rocky planets and complicated chemistry. Some planetary systems surrounding these old stars may have supported life for billions of years, far longer than Earth has. The stars do not spread themselves randomly throughout our galaxy. Instead, they organize into a flattened disk. It is roughly 1,000 light-years thick and 100,000 light-years broad. Our galaxy acts differently than the center and edge, which rotate together and preserve their relative locations. Stars closer to the galactic center have much quicker orbits than stars farther out, like runners on a racetrack, where the inside lanes move faster than the outside lanes. Our solar system, located approximately 26,000 light-years from the galactic center, takes 250 million years to complete one orbit. 250 million years is referred to as a cosmic year by astronomers, and it serves as a good measure of galactic timelines since Earth created 4.5 billion years ago. Our planet has only made 18 journeys around the galaxy in 18 cosmic years. Earth's whole history, from the formation of the earliest rocks to the present moment, is fewer than 20 galactic rotations. Consider how this affects the history of life. When Earth completed its previous orbit around the galaxy 250 million years ago, the supercontinent Pangaea was just starting to split up. Dinosaurs hadn't yet evolved. The most advanced living forms were primordial reptiles and amphibians. Mammals didn't exist. Flowers didn't exist. Grass didn't exist. From their earliest appearance to their end 65 million years ago, dinosaurs lived for around 1/4 of a cosmic year. Human civilization has lived for less than 1/10 of a cosmic year. If our galaxy's history were condensed into a single Earth year, human civilization would be the final few seconds before midnight on December 31st. This sluggish rotation has interesting implications for stellar neighbors. Stars that are currently close together in space will eventually drift apart. From a human perspective, constellation patterns appear to be permanent. We will radically reconfigure ourselves within a few million years. Our sun's orbital route takes us up and down the cosmic disk. As we circle the center, we spend approximately 33 million years above the disk's core plane, then plunge down to spend 33 million years beneath it, causing a gently bobbing motion that takes around 66 million years to complete one cycle. Some scientists believe this vertical oscillation is linked to great extinction events on Earth. When our solar system travels through the disk's center plane, we meet higher quantities of gas, dust, and debris. Debris that might destabilize the outer reaches of our solar system and send comets tumbling toward the inner planets. Stars in different sections of our galaxy circle at varying speeds, resulting in a complicated pattern of stellar motion known as differential spin. At the precise center of our galaxy hides something so huge and dense that it bends space and time. Sagittarius is a star. The supermassive black hole at our galaxy's core has the mass of 4 million suns packed into a space smaller than our solar system. 4 million suns. This gravitational behemoth has such a strong, attracting force that it binds our entire galaxy together. A black hole is formed by the collapse of 400 billion stars into a single spinning structure. This gigantic generates effects that defy conventional perception at its event horizon. Nothing can escape beyond this limit. Space itself is stretched and twisted into inconceivable configurations. Time moves slower than it does here on Earth. Clocks would move slower near this black hole than in your living room. We can't view the black hole immediately because it captures light and everything else that comes too close. However, we can see its effects on neighboring objects. Stars orbiting close to Sagittarius. A star can travel at speeds of more than 3,000 miles per second as it whips around the invisible gravitational anchor. These stars have orbital periods of years, not hundreds or millennia. The black hole occasionally feeds. When gas clouds or perhaps entire stars come too close to its gravitational grasp, as material spirals inward toward the event horizon, friction warms them to millions of degrees. This superheated substance shines brilliantly in X-rays and radio waves before vanishing forever, beyond the point of no return. Recent measurements have revealed that Sagittarius, a star, spins at almost the maximum pace conceivable for a black hole. It rotates so quickly that it drags space along with it. Einstein's theory of general relativity predicts the phenomenon known as frame dragging. This center black hole most likely formed early in our galaxy's history, evolving from a tiny seed by eating gas, dust, and stars over billions of years. As it became larger, its gravitational pull widened, allowing it to absorb and organize the stuff that would eventually form our spiral galaxy. The region immediately surrounding our galactic center resembles a cosmic war zone, with tremendous radiation, strong magnetic fields, and gravitational turbulence, creating conditions that are inhospitable to planet formation and biological life. Dense clusters of huge stars live quickly and die young, exploding as supernovas that add even more energy to an already violent environment. We feel the gravitational impact of black holes, even though we are 26,000 light-years away from them. It serves as the primary anchor point around which our entire solar system rotates. A star, like all other stars in our galaxy except Sagittarius, is only one component of a much larger and more intricate galactic structure. We have an issue that no other astronomer in the universe does. We dwell inside the object we are attempting to examine. Every other galaxy in the cosmos can be seen from the outside, photographed in its entirety, and mapped from a convenient vantage point. We alone must piece together the structure of our cosmic home using evidence obtained while trapped within its confines. Imagine attempting to plan the layout of a large metropolis while trapped within a subterranean apartment with no windows. You could send observers to different street corners to report what they see, but you could never stand back and watch the entire urban area from above. When we look toward the core of our galaxy, we see exactly this. We look through the flat disk that houses the majority of our galaxy home stars and dust. Thick clouds of interstellar material cover our view like fog, absorbing visible light before it reaches our telescope. We can only see a few thousand light-years through this cosmic fog before everything fades into darkness. Radio waves and infrared light penetrate the galactic fog better than visible light, allowing us to look deeper into our galaxy's structure. However, even these longer wavelengths cannot provide the clear, comprehensive perspective that astronomers studying distant galaxies take for granted. Another issue arises as a result of our unconventional viewpoint. When we look down the plane of our galactic disk, we see the brightness of billions of distant stars merging together to form the dazzling band known as the Milky Way. Individual stars become indistinguishable at great distances. We lose our perception of three-dimensional structure and depth. This viewing difficulty, however, has resulted in some stunning discoveries. Because we are inside our galaxy, we can study individual stars far more closely than astronomers. External galaxies are manageable to observe. We can analyze the features of stellar neighbors, map the chemical makeup of gas clouds, and find planets orbiting nearby stars with precision that would be unattainable from beyond our galactic borders. Recent space missions have started to address some of these observational limitations. The Gaia satellite has precisely calculated the locations and movements of over 1 billion stars, making the most detailed three-dimensional map of our galactic neighbors yet attempted. These data reveal star motion patterns that aid in our understanding of the galaxy's overall structure and evolution. Nonetheless, we will never have the luxury of venturing outside our galaxy. To photograph it from a distance, we must remain perpetually confined to our cosmic home. Like creatures living their entire lives inside a massive mansion, able to explore particular rooms, but unable to comprehend the building's overall architecture. This limitation makes our next finding even more astounding, because it involves traits that we cannot see directly, but can only deduce from small gravitational hints. The lovely spiral arms that define our galaxy's appearance are phantom structures that resemble cosmic traffic jams rather than physical objects. Most people think of galactic spiral arms as stationary objects, like the arms of a huge pinwheel whirling through space. However, this image appears to be utterly inaccurate. The spiral arms we see have no permanent matter. Instead, they depict areas where stars and gas temporarily cluster before dispersing back into the larger galactic disk. Consider rush hour traffic on a popular roadway. Cars congregate near construction sites or accidents, resulting in dense groupings that move significantly slower than individual vehicles from an airplane. These traffic jams resemble solid buildings crawling along the road, although no single automobile remains trapped in the jam indefinitely. Cars constantly arrive and exit the packed zone from behind, yet the congestion itself retains its shape and location. Our galaxy's spiral arms function exactly the same manner. Individual stars orbit the galactic center at their own speeds, passing through spiral arms like automobiles in traffic. The arms depict compression waves that sweep throughout our galaxy, resulting in transient concentrations of stars, gas, and dust. These compression waves cause strong bouts of star formation. As they compress gas clouds to higher densities, new stars form bright blue clusters, lighting the spiral arms and making them visible from great distances. The brightest, most massive stars burn up quickly, exploding as stunning supernovae before drifting away from their birthplace. This generates the illusion. The spiral arms have permanent populations of young, brilliant stars. Our solar system is currently positioned between two major spiral arms in a minor protrusion known as the Orion Arm. We last passed through a big spiral arm about 50 million years ago, and will not see another for another 10 million years. As we travel through spiral arms, our solar system encounters larger amounts of gas dust. In addition, radiation may have an impact on the Earth's temperature and biology. The spiral structure of our galaxy rotates far more slowly than individual stars do. This causes differential motion, which permits stars to move in and out of spiral arms throughout cosmic time. If spiral arms rotated at the same rate as stars, they would soon form tight spirals and evaporate within a few 100 million years. Scientists are still debating exactly what causes and maintains our galaxy's spiral form. Gravitational interactions with smaller companion galaxies may pump energy into the disk, maintaining the compression waves for billions of years. Alternatively, the center bar-shaped portion of our galaxy could influence spiral patterns via intricate gravitational dynamics. Recent discoveries have revealed that our spiral arms are remarkably complicated, with branches, spurs, and gaps that evolve over tens of millions of years. However, as amazing as these spiral arms appear, they are only the visible component of something far larger and more enigmatic. Our galaxy is not alone in the cosmic dark. When you zoom out far enough to see beyond our galactic boundaries, an unexpected sight emerges. Little companion galaxies orbiting us like moths around a campfire. Despite being dwarfed by our 400 billion star collection, these cosmic satellites contain millions, if not billions, of their own stars. They dance in our huge galactic home, bound by gravitational threads that span hundreds of thousands of light years. The two most well-known companions shine brightly in the southern hemisphere skies. The large and tiny melanic clouds appear as fuzzy patches of light that resemble detached fragments of our own Milky Way. Early ocean navigators relied on these celestial landmarks for navigation, unaware that they were looking at vast galaxies in their own right. The huge Magellan Cloud, which is 160,000 light-years away, contains around 10 billion stars. The tiny Magellan Cloud, which contains approximately 3 billion stars, is located 200,000 light-years away. These distances position both galaxies far outside the observable star disk, but yet within our wide dark matter halo. These neighboring galaxies don't orbit in peace. However, our immense gravitational effect changes their shapes, stretching and distorting their star populations like taffy being dragged. Long streams of gas and stars are pulled away from both Malin clouds, leaving massive ribbons of matter trailing behind them as they round our galactic center. However, the Malin clouds are merely the largest members of a much larger galactic family. Our neighborhood is home to over 30 smaller satellite galaxies, the majority of which contain only a few million stars each. These small galaxies have unusual names like as Draco. Sculptor and Forks are called for the constellations in which they appear. Many of these satellite galaxies are so faint that we only recently discovered them by detecting their weak glow against the background stars with sensitive electronic detectors. Some have so little regular matter that they are virtually entirely composed of dark matter, making them nearly hard to detect. Despite having the mass of millions of suns, our gravitational pull on these companions is destructive over cosmic time. As they circle across our extended halo, tidal forces eventually remove their outer stars, allowing our galaxy to grow. We are gradually cannibalizing our smaller neighbors, becoming larger at their expense. Galactic cannibalism, which has been going on for billions of years, shows something important about how big galaxies like ours develop and grow. You can only glimpse the glowing core of something far larger and almost completely invisible. Recent observations show that our dark matter halo is roughly 2 million light-years from our galactic core. This suggests that the true limit of our galactic home is 20 times longer than the visible edge of our star disk. The vast majority of our galaxy is empty space filled with invisible matter that we can only detect due to its gravitational effects. Imagine our visible galaxy as a cherry pit in the heart of a basketball. The cherry pit represents the 100,000 light-year disk that contains all of our familiar stars, gas, and dust. The basketball symbolizes the full extent of our cosmic domain, which is packed with dark matter particles that interact with nothing except gravity. This invisible halo has at least 10 times the mass of all visible matter in our galaxy combined. There are 600 billion to 3 trillion solar masses of dark matter. Surrounds us in a nearly spherical cloud that dwarfs anything we can see. We exist inside this quick, invisible structure like deep-sea creatures in the lit zone of an ocean that extends far beyond their perception. The dark matter halo influences the behavior of everything inside its borders, including satellite galaxies, orbits through this invisible medium, subject to gravitational forces from matter. They can't observe or touch our companion galaxy's orbital patterns. Trace the true gravitational architecture of our universe, exposing the presence of dark matter via their motions. Recent computer simulations suggest that our dark matter halo is made up of thousands of smaller subhalos, dense concentrations of invisible matter that flow through the main structure like schools of fish swimming across the ocean. Some of these subhalos may be large enough to catch normal matter and produce small satellite galaxies. Others remain perpetually dark, made up solely of particles that never interact with photons. This wide dark matter envelope governs our galaxy's interaction with the larger cosmos. The halo's gravitational pull reaches out to grab gas falling in from intergalactic space, supplying the raw material for further star formation. It also protects us from some of the fury of the universe by deflecting high-speed particles and smaller things that would otherwise disturb our galaxy's delicate structure. The boundary between our dark matter halo and intergalactic space is still not well defined. The density of the halo reduces as one moves away from our galaxy's center. It eventually becomes so thin that it merges silently with the overall dark matter background that fills all of space. But even this massive unseen structure is only one component of a far larger cosmic edifice. Our galaxy is not the stable, perfectly balanced disk that most people envision. Instead, our cosmic home wobbles and flexes like a spinning coin, gradually losing speed. The outside borders of our galaxy disk stretch up and down, causing ripples that spread inward toward the center like waves on a disturbed pond. This warping motion is one of the most dynamic and unexpected features of our galaxy's structure. Recent investigations with variable stars of various ages have indicated that our galaxies bend or rotate. Every million years, it moves backward by around 12/100ths of a degree. This indicates that the warp pattern steadily rotates around our galactic center in the opposite manner. From our star's orbital velocity. What is the reason of this unusual wobbling motion? The culprit seems to be our dark matter halo. Computer models imply that our invisible halo is slightly flattened. It's more like a football than a perfect spherical. As our star disk rotates within this oblate dark matter dispersion, gravitational interactions provide the wobbling motion we see. Imagine a coin spinning on a table. As friction slows the coin's rotation, it begins to wobble more and more noticeably, eventually falling flat. Our galaxy undergoes comparable dynamics, except instead of friction, we have misalignment between our rotating disks, and the principal axis of our dark matter halo generates the torques that propel the wobbling motion. This galactic wobble has an impact on everything in our universe. Stars in our disk's outer regions experience vertical acceleration. As they ride the warping waves, gas clouds compress and stretch as the disk bends around them. Even our solar system is relatively near to the galactic center, participates in this stately, cosmic dance. The wobbling motion also reveals important information about the distribution of dark matter throughout our galaxy. Astronomers can determine the form and orientation of the invisible halo that dominates our galaxy's mass by monitoring how warp events occur. This provides one of the few direct techniques to investigate the properties of dark matter on a galactic scale. Satellite galaxies complicate our galactic wobble. The huge and small Malin clouds, as well as our smaller companion galaxies, have their own gravitational influences on our disk structure. Their orbital motions provide additional torques, altering the rate and pattern of our galaxy wall. This study demonstrates that our galaxy is in a permanent state of dynamic change, responding to gravitational pulls from visible and unseen stuff. However, our wobbling disk confronts an even more dramatic future transformation. 4.5 billion years from now, one of the most stunning events in cosmic history, the Andromeda Galaxy, will reshape our night sky. This massive cluster of 1 trillion stars is racing toward us at approximately 250,000 miles per hour, colliding with our galaxy in what astronomers refer to as the most predicted cosmic catastrophe. The merger will transform both galaxies beyond recognition, forming a new cosmic structure from the remnants of our current universe. Andromeda currently looks as a small smear of light in our fall sky. It is barely visible to the human eye, despite having more stars than our entire galaxy. However, this seemingly fragile spiral is only 2.5 million light-years distant, making it the closest big galaxy to our own. In cosmic terms, we are nearly in the same neighborhood as Andromeda approaches. Its gravitational effect will begin to damage our galaxy's structure long before the collision occurs. Our outer spiral arms will stretch and distort streams of stars, pulling them out from both galaxies and forming huge bridges of matter, bridging the distance between the two cosmic titans. The collision itself will occur over billions of years, a slow-motion catastrophe that spans timescales beyond human comprehension, despite the fact that they contain about 1 trillion stars in total. Individual star collisions will be extremely infrequent due to the huge distances between each point of light. Instead, the collision will resemble two clouds of fireflies moving through each other, with gravitational interactions disrupting the orbital trajectories of most stars. Our Sun is likely to survive this cosmic merger. Though its fate is unknown, computer simulations predict that our solar system could be thrown into the outer reaches of the merging galaxy, or even expelled totally into intergalactic space. Earth may find itself orbiting a star that travels indefinitely between galaxies, with no galactic home to call its own. During the merger, the supermassive black holes in the centers of both galaxies will spiral inward toward one another, eventually uniting into a single gravitational monster with the mass of more than 5 million suns. This black hole merging will produce more gravitational waves than our Sun will emit in light over its 10 billion-year lifetime. Instead of two magnificent spiral galaxies, the resulting merged galaxy, known as MIL by astronomers, will bear no resemblance to either of its parent structures. The collision will result in a single elliptical galaxy, a roughly football-shaped collection of stars without any organized structure or spiral arms. But this collision is only one illustration of the hostile cosmic environment that surrounds us. Our entire local galaxy group, including the Milky Way and Andromeda, travels 600 miles per second through space towards something big and enigmatic. That depicts our collective velocity toward a gravitational anomaly known as the Big Attractor. This unseen mass concentration is located approximately 150 million light-years away, in the direction of the constellations Hydra and Centaurus, buried behind the dust and stars of our own galaxy disk. The enormous attractor has a gravitational attraction on thousands of galaxies over hundreds of millions of light-years. Its influence is so far-reaching that it affects the velocity of our entire cosmic neighborhood, drawing galaxy clusters and superclusters towards itself like garbage caught in a cosmic whirlpool. What could be large enough to gravitationally govern such vast expanses of space? The huge attractor has the mass equivalent of tens of thousands of galaxies like our own, concentrated in a region about 500 million light-years across. This is one of the greatest structures in the known universe, a gravitational anchor point that influences the motion of matter over huge cosmic distances. The puzzle deepens since the larger tractor is partially hidden behind our own galaxy. When we look in that direction, the stars and dust of our galaxy disk obscure our vision of what lies beyond astronomers. Call this the zone of avoidance, an area where observations become extremely difficult due to obscuration by our own cosmic home. Even with telescopes capable of seeing through dust, astronomers have discovered numerous enormous galaxy clusters in the direction of the main attractor, the Norma cluster. The Centra cluster and the Hydro cluster all contribute to the gravitational pull that governs our movement through space. However, integrating all of these visible structures does not account for the overall attractive force that we observe. Something else must exist. Additional mass, maybe in the form of dark matter concentrations or hidden galaxy clusters, contributes to the gravitational impact of the big tractor. The total amount of matter responsible for our cosmic motion is unknown, buried behind the veil of our own galaxy's obscuring material. This revelation demonstrates that our galaxy does not travel randomly through space. Instead, we follow the gravitational currents created by the universe's greatest structures.